Good evening, Bhavya.
Good evening, sir.
Is there any class?
Sir,
Any classes going on now?
as sir, no, sir, completed, sir. 15 minutes back itself, class is completed, sir.
Okay. Today, we'll discuss about finite state machines. So, in the last class, already we have discussed about state diagram, state machine, state diagram, state equation, state chart. So, three things. So, generally, to design any FSM, finite state machine, these three are important. Of course, one is the state equation, next one is state table, next one is state diagram. So these three are important. So when it comes to the finite state machine, what do you mean by finite state machine? So generally we have two different types of finite state machines. One is the Moore finite state machine, one more is the Melee finite state machine. Two things. See, here is a all state machines have the general feedback structure consisting of. So this is the, if you take this one, this picture, if you see this picture, this. See, here is a, this is the input and this is the maybe current state or output you can say. So here is a two things are there. This is the next state logic, this is the memory logic. So for this, the next state, let me see here, the next state is depends on the present state of inputs as well as the what current state. Okay. The next state, okay, of the machine is formed from the current state and the current inputs. Sequential logic holds the value of the current state. Generally, here is the what is the next state logic, what is the memory logic, what is the present state logic. Generally, memory is the sequential logic. This is the combination logic. That is. So output logic. Generally, one more thing you need to add here. That is the output logic. So the output logic is again combination logic. Yes. Yeah. So this is the Moore state machine. In the Moore state machine, so as I told you, three things are there. Three blocks are there. One is the next state logic. One more is the state resistor. One more is the output. So I can write this as, I can name this in different manner. So how means in this diagram I can say this is the next state logic. It must be a combination logic circuit. And second one is I can say this is the state updation circuit. State updation. State updation, generally it is a flip-flop. State updation is generally flip-flop. Flip-flop, you know, it is a sequence circuit. And then last one is the output logic. This is again combination logic. So three stages, 1, 2, and 3. Okay, the first one is next state. Second one is state updation. Next one is what? Combination logic. Output logic. So first and last are the combinations, and the middle one is the sequential. So here, if you want to write the logic expression for the next state. So because we have two inputs for this block, we can write as next state is the function of current state. This is the current state. Yeah, this is the current state, as well as inputs. Similarly, for the output here, only one thing is there here, that is the current state. So next state is a function of inputs as well as current states. and output is a function of only current states. Only current states. So this is the what more state machine. So the difference between the more and Melee state machines are very simple. So here, if you see these two equations, one minute. So I can show with these two equations the difference. See, the first equation for the next state and the second equation for the output state. If we compare with the Melee state machine, see, the first expression is as it is. In the second expression, what inputs also came into the picture. Earlier in the Melee machine, output is a function of only current state. Now it is a function of current state as well as inputs. So for that, the circuit is, you can change like this. See, here is the output. The output is not only depends on the current state but also inputs. So only the thing is, in the earlier case, this is not there. This path is not there. Just this is the path. Now the path is added like this. So that is the difference between the Melee and more state machines. I hope you understand. So in more state machine, what happened? 1 minute, I will clear the text. See, here is in this one, this is the next state. This is the state updation. This is the output logic. Okay, so here the next state is function of these two, and output is the function of only this one. When it comes to the Melee state machine, yeah. So since the inputs are directly fed to the output logic, this is the next state logic. This is the state updation. This is the output logic. Same thing, no change. But only the path is inputs are fed to the output logic. So that's why this expression only changes, remaining as is. Okay. So the differences between these two are, I think, not required much more. But what is the advantage of these state machines? So we will discuss now. Yes. Yeah. So as I told you, the more state machine, I will explain first more state machine. MOO or more. So FSM, otherwise you can say FSM. Okay. As I told you, for example, this is the 1 minute. I will put 1 minute. This is the one block. This is one more block. And this is one more block. Yeah. So now this is the input. Say the input sequence for machine is, let us say W. And output, this is nothing but the, so next state. Okay. I can say this is the small y. Okay, this is the combinational logic circuit, which is the next state logic it has. It holds the next state logic. And this is the state updation. So it is nothing but a flip-flop. It is a sequential. So the last one is the output logic. So this is the current state. This is the next state. You can say small y is what next state. And this is the capital Y. You can say capital Y is equal to, so current state. And this is the output. You can write output as Z. This is once again combination logic circuit. So flip-flop is required clock. This combination logic doesn't require any clock, so that this is the clock is applied to the flip-flop. And so the current state is connected to the input side to find the next state. Yes. This is the simple diagram for the most state machine. Okay, so here my question is, as I told you, we have three things. One is what? Here is important things. First one is, because of three blocks here, we need three procedural blocks. Need 1 minute. So need three procedural blocks. Yeah. So one is first question block is take this one. Next state. Next state. Next state. Combinational. Next state. Combinational circuit. Combinational logic circuit. Second one is state updation. State updation. Second one, state updation. Updation. It is a sequence circuit. Sequential logic circuit. And last one is so output combination logic. Output combinational logic circuit. So three blocks are there, so that we need three procedural blocks. Procedural blocks. Yes. Suppose I will take on an example. Here my question is very simple. Design a more FSM file state machine to read a binary sequence. To read a binary sequence. To read a binary sequence. Sequence name is W. Yes. And sets output Z is equal to 1 if either A 110 or A 101 pattern finds. Pattern finds. So that's it. This is my question. Design a more FSM to read a binary sequence. W. W is the binary sequence. In that sequence, if you find the sequence of bits is like this or like this, the output must be equal to 1. Okay, otherwise output is 0. So first of all, as I know, first of all, what to do? State diagram should be drawn for this one. How the state diagram is drawn? So because we have, so this or this is the two patterns as given. For any sequence, any order of the sequence, in the input bit stream, if you find continuously this or this, output is logic 1. That is 1. Okay, for that, first of all, I will start with one state. Let us say state A. I will put what is the A letter. Then first of all, A. When I am here, so state A. Yes, this is the clear CLR, clear signal. Okay, so whenever clear is 0, it starts from the A. Okay, first state. Suppose if the input bit stream, in the bit stream, input bit is 0, so that if the input bit is 0, it should be say at the same state. Yeah, this is. If W is input, W means input bit is 0, then it should be at the same. So next state is B, let us say. Suppose if input bit is 1, input bit is 1. So whenever you are at A state, the input bit is 1, go to the B state. So that W is equal to 1 means go to the next state is B. Okay, this is the next state. For A, next state is B. Suppose take one more state, C. So when you are at B, okay, if the input is 1, So the next state should be C. 1 1. Yeah, C 1 1. So next one is D, state D. State D. So if the input is 0, if the input bit is 0, 1 1 0, 1 1 0, so W is 0. The next state is D, and we should make output Z is equal to 1. Okay, this is one case. Suppose whenever you are at the state B, if 1, the next state is C. Next state is C. If it is 0, the next state should be so E. Yeah, consider one more state and connect like this. So you should go from B to E if input is 0. 1 0. Okay. 1 0. Yeah. Next one is, suppose you are at C. You are at C. If next state, if the input is 0, next state is D. If input is 1, next state is same thing. So W is equal to 1. W is equal to 1. Okay. So the next one is, suppose you are at state E. If the next state is 1, 1 0 1, 1 0 1, next pattern 1 0 1. If it is 1, then take one more state. W is equal to 1. 1 0 1 means Z should be 1. So that now I can write. So Z is equal to 1 here. So Z is equal to 1 here. Z is equal to 1. Okay. Suppose from the E, if the next state is 0, if the input is 0, the next state should be A. W is equal to 0. 1 0 0. 1 0 0. Nothing will happen. 1 1 0 1. 1 0 1 is again 1. Output is 1. Okay. So next one, if from F, suppose if W is equal to 0, then come to back. E is the next state. Similarly, from F, if W is equal to 1, if W is equal to 1, then go to the C state because 1 1. Okay, it maybe goes like this. Suppose here is 1 means W is equal to 1 means it comes to here. Suppose here D at the 0, then comes to original state. So now I can define what is the A, what is the B, what is the C like that. So A is equal to B is equal to C, D, E, F. So 5, 1, 2, 3, 6 states I have defined. A is nothing but all zeros. B is nothing but 0, 0, 1. And C is nothing but 0, 1, 0. And D is 0, 1, 1. And E is 1, 0, 0. And F is 1, 0, 1. So remaining, so only 6 combinations we used. So 2 more combinations are there. One is the 1, 1, 0 and 2 ones. These combinations we are not using. Okay. So look at this one. This is the way of drawing the state diagram for the given problem. Here is he is required. So what we require? We require to make the output Z is equal to 1 whenever we find the particular sequences of bit patterns. So either this sequence or this sequence, if you find continuously, then Z is equal to 1. So that this is one of them. 1 minute. So this is the one of the path to reach the Z is 1. Otherwise, one more path is either this one also one is path to find to make the output Z is 1. Okay. So from this I can write the state. Vanilla code. First I want to write the module. You can start with module. 1 minute. How to write the code? 3 procedure blocks I will use. 3. So module. So maybe it's a more machine, M-O-O-R-E, more. You can write like this, more underscore 1. You can write underscore 1, more underscore 1, brackets. Write the ports. What are the ports are there? Clock, clear, W and Z. These are the ports. Yes. So what are the inputs here? Input ports are clock, clear, W are the input ports. So output ports are Z, output and resistor also. So output space resistor Z. Okay. So one more thing I required for the what states A, B, C. So that's why I will write the res 2 down to 0, 2 down to 0, 0 to 2. That means small y and capital Y. These are the state variables generally. So these are the state variables. So because in the circuit here, small y and capital Y, these are the state variables. Small y is at the next state and capital Y is at the current state. These are the state variables. So that I can write here state variables. Yes. These two are the state variables. Okay. So now parameters are required because A, B, C, D, E, F. So we want to define. So local parameters, you can write local parameters or parameter, you can write whatever it may be as you like. So local, so parameter. Okay. So A is equal to, what is the A value? 0, 0, 0, 3 zeros, comma. What is the B value? 0, 0, 1. What comma? What is C value? 0, 1, 0. What is the D value? 0, 1, 1, comma. And E value is just 1, 0, 0, comma. And F value is, F is 1, 0, 1, and this is the parameter. So definition. So generally these are nothing but 1 minute. So this is nothing but state assignments. State assignments. These are called these things. This is called the state assignments. Assignments. Okay. Now come to the next state logic. First 3 logics are there, so that we'll start from each logic. First procedure block is next state block. Next state combination logic, otherwise you can say whatever it may be. This is a comment only. So in the next state, so how can you define the next state? I will go to the next one. Yeah, here. Always at the rate of small y is the next state, comma, W is the input. W is input. Now I will use the case statements. Case expression is small y. Small y. If y is what? It may be A, y may be A or B or C or D or like that. So first I can write like this. Suppose A. Case statement is, case expression, case statement is A. If W, suppose you are at A, state A. If W means W is equal to 1, go to here. So whenever you are at A, if W is equal to 1, go to B state. Next state is B. So that you can write the next state is, so capital Y is equal to B. Else Y is equal to A only, same thing. If 1, next state is B, otherwise same state. Okay. So now if suppose you are at B, if W, again go to the state diagram. B, 1 means C, 0 means E. Yes, Y is equal to C, else Y is equal to E. Yes. So next C. If W, again check it. Suppose you are at C state. So current state is C. Then if W is equal to 1, input is 1, then what? Next state is C. Next state is C. Yes. The next state is what? D. Next you can take the D. If W, what is the next state? So next state is F. Otherwise, else Y is equal to A. Similarly, you can write for the E. Okay. If W, so Y is equal to F. Else Y is equal to A. The last one, F, if W, so Y is equal to C, else Y is equal to E. Yeah, all states are over, but out of 8 combinations, we used only 6 combinations, remaining 2 combinations not used, so that default case is required here. So I will write here default. So default, what is the default? So Y is equal to 3 bits, X, you can make it. Yes. Now we started with the case, so that it must be ended with the keyword and a case. This is the one of the procedure block. So generally, all these statements are used for the next state. These all statements are for the next state specification, which depends on what? Small y and input W. Now this is only one procedure block. 2 more are there. One is, this is for the state, next state logic. Now 2 more things are there. One is for the state updation, one more is for the output. Okay. So now for the state updation. State updation. State updation is a sequential logic circuit. Sequential logic circuit. Okay. So now I will write here. In the state updation, always at the rate of negative edge of clear, neg edge, CLR, ORR, a comma, you can take anything. So positive clock, CL. Yeah, this is. Now, if so, because of second one is a state updation circuit, second block is a state updation block, where it depends on the clock, so that clock and clear, so that I can take if CLR clear not, that means if the clear is not 1 equal to 1, if clear is 0, it's nothing but clear is 0, then your small y is equal to yes A. It start with the beginning. Okay. Now else, otherwise, if not, if clear is equal to 1, then small y is equal to capital Y. Okay. So this is these statements will use for the what? State updation, either same state or next state. Same state or next state. Okay. That depends on the same state or next state depends on the what? Clock and clear signals. Clock and clear signals. Okay. So this is the yes. Now third procedure block is output. Define output. So define output. It is a combinational logic circuit. So If the sequence, if you find the sequence 110 or 101, definitely output should be equal to 1. So that always, you can write always block, always at the rate of, yes, small y. Small y means what? So next stage. Okay. If bracket small y is equal to d, what is the d? D means 110. 110. D means 110. And one more case is or. This is the or in. Okay. So what is that one? One more case, y is equal to f. Two cases. D means 101. Sorry, D means 110. F means 101. So now, if this is true, then z is equal to 1. Right here, z is equal to 1. Otherwise, if it's false, else write z is equal to 0. So end module. And this is the complete Verilog program for this problem. What is one? So input bit stream is coming. If continuously in an order, suppose 110 or 101, if you got, that machine should produce the output as high. Otherwise, the machine output should be 0. So to design this machine, so you can start with some assumption states. So A, B, C like that. You can start if input is 0, assume. Stay at the same state. 1 means go to the next state B. Okay, from where? If 1 means go to the next state C. Otherwise, if 0 means go to the next state E. Okay. So from C, if the next state is 0, go to the D and make the output as 1. So if the input is 1, then stay there only to wait for the next time whether you will get the 0 maybe. Okay. So like that, first you shall complete the state diagram. Then A, B, C, D, E, F. These are the states assigned with some numbers, binary numbers, encoded with the numbers. Okay, since 3 bits you are using to represent each state, so but we have 8 combinations. Out of that, only we are using only 6 combinations, so that 2 are not using. So that in this program, while writing the program, don't forget to add the default case. So otherwise, so what happened? Other than this combination, it comes. It doesn't know what to do. So that's why, if other than this combination means either this or this comes, then it will take some action. Now for that, as I told you, as in the picture, we have 3 blocks. So next state block, state updation block, and output block. For each block, one procedural state. Each procedural block is required. For each block, one procedural block is required. So that I will start with one procedure. First of all, this is the whatever. All these are the code declarations and all these things. And here is local parameters are required to what is that one to make A, B, C, D. What is that? Then you can start the first procedure block next state, second procedure block state updation, and third block for the output. This is the one more state machine. So I think everybody is understanding. But here we can make it simple. So because here initially in the first case, what I told you. So 3 procedural blocks are written separately. But we can have a provision to club 2 procedural blocks or 3 like that. For example, in the second case, I can change like this. The second type, same problem. So here I can next state and output. Next state and output logic. Procedural blocks can be merged. So how can you merge this one? See, I can, for example, same header should be there, a module and everything. So now I can write like this. 1 minute. Yes. So that means module more more underscore 2. You can write all the things, and all the things you should complete first of all. Then you can start the always block as usual, always at the rate of what is inside the bracket. So generally, so y and w is there. Y, small y, comma w. This is the first one. So begin, yeah, begin. Case y, small y, yeah. So remaining story, after that case, what we should write here is already there. The first, this is the same story you should write until, so default, until default. Okay, so next, after the default, you can write the end case or end case also. Then whatever the output logic, output block here is there, output block. This should be written here. This should be, we can match with this. So how means and complete. Here is the, what is that one? End module, end case, end case. Okay, so later write if in brackets small y double equal to d, or in with the small y double is equal to f. That is the logic of output. Okay, then z is equal to 1. So otherwise, that means else z is equal to 0. Then you can make it end. Yes. So these two are merged. Only the, what is the main state updation block is there. This can be written as it is outside of this block. That is one type of writing the Verilog code. And another way is also there. Some third way. So in this third model, you can write the next state specifications means first block, and state updation both can be keep in the same block, same procedure block. So both can be in the same always block. Yes. Now you can write the same story like what is that one? Module. So more _3, the story, everything same declarations. Then you write always at the rate of, you can write what is that one? Negus clock, negus clear, neg edge clear, or pause edge clock. Yes. Now I want to write here one thing, that is the state updation. First I will keep the state updation, that is if clear is 0. If clear is 0, then small y is equal to a. Yes. Else then start the case small y. Then start the same thing, A, B, whatever the statements. So A, B, C, I will write here. So D, E, F, then default, everything as it is. So default. So end case. So finally, you can write assign, assign. Okay, Z is equal to, assign Z is equal to bracket small y, this is output, small y is equal to B, or in with small y is equal to F. Okay, so question mark, if it is true, your Z is equal to 1, question mark, Z is equal to 1. So otherwise, your Z is equal to 0. Yes, this is. So end module. Yes. So in the last statement, output equation, everything is kept in the only one block, one procedure block. So assign Z is equal, conditional statement I use here. It's assign Z is equal to the logic. If the logic is 2, Z is 1, otherwise 0. That is. So this is the design of the more state machine, I hope you understand, everybody. So once again, I'm going to start with the more state machine. This is the more state machine. So there is a next state updation and the output logic. So since there are three blocks, three procedure blocks is better always without confusion. So one example, if I take the one example, like to find a sequence, if you find that sequence in the bit stream, make it the output as one. Here is two sequences there, either one is valid, it becomes one. So that we can start to draw the state diagram. So this is the state diagram. With the state diagram, the states can be assigned with some binary numbers, okay, some code. So you should confirm that all the combinations used are not. If any combination is left, then definitely default case is required. Then start. This is the module and the code declarations and the parameter declarations. Then start with the next state logic. This is one procedure block. Next for the next state. This is the two procedure blocks. One for the state updation, one for the output logic. So the same three different procedure blocks can be combined. So next state and output can be combined. Next state and state updation can be combined. In the second, this is second model. The next state and output logic both are combined. Both are in the same block. So and in the third one, so next state updation, and also what is that one output logic, all are kept in the same block, procedure block. This is the three different ways. I hope you understand. So students, any doubt? Students, hello, students. Okay, good. So now I will stop this sharing of this. Yeah, this is my program. Yes, this is the state machine program. Yes, this is my state more machine. Here, this is my program. I wrote here. So here is that. So input is clock, reset, sequence in. Input is the sequence in. So the bit stream you can apply here. The bit stream you can apply here. So output is the, of course, you can take the detector output or whatever maybe. So now parameters. So first 0, 0, 0, 1 means 0, 0, 1. That means you can say in place of this one, I can write the ABCD. I wrote there ABCD. Now you can write 0, 1, 1, 0, 1, 0, 1. Okay, and 1, 0, 1, 1, 0, 1, 1. So like that, I wrote like this. So these are states. These are the states, and I think current state and next state must be registers. Okay, this is the first one declarations. Now come to the always posage clock or posage register reset. So here, so you can start with then if reset is equal to 1, if reset is equal to is double equal to 1. So both sides must be equal. So then current state is equal to 0. This is not the assignment. This is the equality condition statement. Okay, then current state is equal to 0. So like that, for each state, I wrote this one. So later, my test module is, my test bench is this is, the test bench is this one. Okay. So, and if you want to see the, yeah, if you want to see, here it is. Yes. Yeah, here is the schematic. The schematic is this one. For this machine, this is state machine, and this is the where is output? Yes. Yeah, you can run now. You can run simulation. You can go for the run simulation. If you run it, so I can get the output. I can get the output. Yeah, this is my output. See, here is I can. Yeah, this is. Yes. Let's see here. So here my detection is this is the for the this one generally. Yeah. So this is my problem. Oh, okay. So 1 minute. Yes. This is the problem. Yes. What is that? Yes. So the more FSM keeps detecting the binary sequence of 1011, I want to make output 1 whenever the 1011 sequence I found in the input binary sequence. So for this is the code. We implemented this one. Okay. Yeah, here you see. If you see this one, yeah, you can go with this one. Yeah, see this one. I want to just zoom in. Yes. So this is the first one is the clock. This is the data in. The first one is data in. Okay, sequence. Second one is clock. Third one is reset. See this one. This is the data out is 1. Whenever the input sequence is 1, 0, 1, 1. See, this is the input sequence. 0, 1, 0, 0. Sorry, 0. Oh, sorry, 1, 0. This is 1. This is 0. And this is 1, 1. For this combination, whenever the input bit stream is having this sequence, then your data is, see, here is 1. Okay. Here. Yes. 1. Otherwise, data out is 0. This is the sequence detector. So generally, FSMs are used to find the sequence detectors. So this is the. So students, do you have any doubt? Hello. So if you don't have any doubt, then do one thing. Whatever the program I explained in this lab, this is. So this program, you should do one thing. Write the test bench for this program. This one. Yeah, for this program, write the test bench and execute and show it in the next lab class. Okay, anything? Bhavya?
Sir, yes, sir. Yes, sir.
సో అర్థమైందా?
Yes, sir.
ఇవన్నీ నోట్ చేసుకున్నారా లేదా స్క్రీన్ షాట్స్ తీసుకున్నారా?
Screen shots తీసుకున్నాను sir.
అది వెరీలాగ్ ప్రోగ్రామ్ కూడా తీసుకున్నారా?
Yes, sir.
మొత్తం చూపించి తీసుకున్నారు కదా? So then the job is, what is the job is? So for this I wrote the design module. You write the test bench for this one.
Okay, sir.
So I already given the 3 cases. three models, first, second, third one. For the three models, of course, test bench is same, don't worry, but we should write three models. The first model, three separate procedure blocks for each block. Second, so next state and output should be merged. In third, all are merged in the single. Okay.
Okay, sir.
Yeah. So then I will stop here. Already time is over. So anything to discuss, students? If you want this very large program, this one 1011 sequence, then this is the code, test bench and code. This is the test bench. If you want, you can try. You can take the snapshot. Test bench. Yes. So if you want module, design module, yeah, this is design module. Yes, this is design module. Always. This next one is this one. Next one. State updation. Yeah. So can I stop here?
Yes, sir, thank you.